Hello. In this video, we're going to continue our exploration of infinite sequences and more specifically the convergence and divergence of different examples of sequences. And really this video is going to be focused on giving you a couple of techniques for understanding and analyzing sequences to decide whether they converge or diverge. So I've picked a motivating example to show you what L'Hopital's rule is all about. I've picked an example of a sequence an whose terms are defined by this ratio. So the nth term is n squared divided by the exponential e to the n. Now in this example, as the n, the index, the term of the sequence grows and grows, the numerator n squared, that gets bigger and bigger and bigger, and the e to the n, the denominator, also gets bigger and bigger and bigger. And so this essentially is approaching some kind of like infinity over infinity situation. As I take a limit as n goes to infinity of n squared over e to the n, well, both of those things are getting bigger and bigger. And so that's why I'm using this quotation marks around the infinity over infinity situation. And in a Calculus 1 course, you've probably called this an indeterminate form because I'm not allowed to, I almost hate myself for even saying this, but I'm not allowed to do some utter nonsense like I'm about to do, which is to cancel the infinities and say this equals 1. Oh gosh, that hurts my heart so much. Please don't do that. So instead, what can I do? Well, let's try to understand what L'Hopital's rule is really doing, which I'm about to apply on the next slide after stating it. Here, this example, this table over here on the left, is going to show you and teach you a little bit about why L'Hopital's rule actually works, what it's doing. So what I'm doing in this table is I'm setting out n, the index of the sequence. So this is saying the first term, the second, the third, the fourth. Then eventually I start making them increase more, the 10th, the 20th, the 100th, and the 1000th, and so on. And then, sorry, the next two columns are the numerator and denominator of that ratio. So the top is n squared, that's this column. The bottom is e to the n, that's this column. So I'm calculating those two numbers separately. And then I'm showing you what their ratio is. So this really, this final column over here, this is the sequence an itself. This is the sequence an. And notice how they seem to, those values seem to be growing a little bit at first, and then they start to decrease a little bit, and then eventually they're going to get wicked tiny and really close to 0. So why is that happening? As I make n bigger, n squared grows and grows. I get 2 squared, 3 squared, 4 squared. Those are getting bigger and bigger and bigger, naturally. But e to the n is also growing. E to the 1 is e itself, so that's e right there, 2.718, and so on. This is e squared, this is e cubed, and so on. And so as I take larger powers of e, those numbers also grow. But in their ratio, notice that the e to the n eventually grows much faster. So like right here, they're pretty close. Here, they're fairly close. But then eventually, the e to the n is like way, way, way bigger, many more digits. And it becomes not even comparable anymore. And what's happening down in the bottom rows is that e to the 20th is such a big number that it's not even displaying to you all of the decimal points. So this e to the negative 7 means that that's 0.6 zeros and then an 8. And then this one down here means it's, I can't even write them all, there are 39 zeros and then a 3, 7, 2. And then the bottom row for n equals 1,000, I actually almost broke Excel by asking it to calculate e to the 1,000. It's such a big number that it can't even do that, and that's what the hashtag num means. It just says, sorry, that exceeds my capabilities. So this ratio is really converging to 0, 0. The limit of this sequence, n squared over e to the n, is 0. This is convergent. And the reason that's happening is because I have an indeterminate form. The top and the bottom are both going to infinity, but the bottom is going to infinity so much faster that it wins out in the long term. And their proportion, their ratio, is going to shrink down to 0 really rapidly because of how much faster e to the n goes to infinity. That's literally what L'Hopital's rule does. This is not some dark calculus magic, although it may feel like that sometimes. L'Hopital's rule says, if you have a ratio where the top and the bottom are both going to infinity, figure out which one is going to infinity faster. If I have a limit like this, and let's say they're both, the top and the bottom are approaching infinity, then what is it exactly that this ratio of f prime over g prime is doing? What does that represent? Remember that a derivative is a rate of change, a growth rate, how rapidly a function is changing. So if I have a situation where the top and the bottom, f and g, are both growing to infinity, and I want to figure out which one's growing faster, doesn't it make sense to look at their derivatives? Which one has a larger derivative? Which one is growing to infinity at a faster rate? That's exactly what this other limit does. And L'Hopital's rule says if you look at that, it will tell you what the original limit was doing. So jump down here to the bottom where I'm applying this rule to the example we were just doing on the previous slide. I would recognize an infinity over infinity situation from that example we were looking at, and so that's why I've written a LH here to say I'm applying L'Hopital's rule in the next step. So you don't have to figure out where that equals what I was doing there. I'm reminding myself and anybody reading that I'm applying L'Hopital's rule. And notice how I'm taking a derivative separately in the top, n squared becomes 2n, and I'm taking a derivative separately on the bottom, but the derivative of e to the n is just itself. As n goes to infinity, what does 2n do? That also grows to infinity. So I have another infinity over infinity situation, and I can apply L'Hopital's rule again by taking a derivative of the top, which is 2, and then the bottom, which is still e to the n. And now finally I have a situation where I have a fixed number, 2, a constant, divided by something that's growing to infinity, and that's what's going to make it go to 0. If I have a fixed constant number like 2 divided by a growing function that gets bigger and bigger and bigger, then those ratios, those fractions, are going to go down to 0. This statement in the theorem box up at the top says you can do something like this L'Hopital's rule application, as long as you have an indeterminate form like infinity over infinity from that example, or even 0 over 0, that works too. If I have a function going to 0 and another function going to 0, what does their ratio do? Well, it depends on which one is going down to 0 faster. That's why we look at the rates of growth, the derivatives. Here's another technique that may show up in some examples. Let's consider this specific sequence example that I have defined at the top, an. It's given by sine of n over n. Does this sequence converge or diverge? Pause the video now, explore some examples by plugging in n equals 1, 2, 3, 4, maybe all the way up to 5 or 10. See if you notice any patterns. What do you observe that you can state? And what do you wonder? Or you have any questions? Are you wondering something about it? And just a real quick note, remember that when I say sine of n, we're always assuming the input of the sine functions in radians. So by the way, it's actually not even apparent what the real pattern is for the numerator. If sine of 1, sine of 2, sine of 3, those aren't particularly nice numbers, because that's like the sine of 1 radian and 2 radians and 3 radians, and those are not nice multiples of pi. So it's not even obvious where those are around the unit circle, if they're following any particular pattern. So keep that in mind and make sure your calculator is in radian mode. And by the way, this is a Desmos graph that you would get by visiting this URL that I have pasted down there. This is a way just to show you the same information you're probably calculating out with your calculator on paper. Here is a plot of the terms of the sequence. So you can see that green dot right there at x equals 1. That's the first term of the sequence. That's sine of 1 divided by 1. So you can see how it lives on the curve given by this a of x function that I've graphed here, the sine of x over x. So at x equals 1, that's the first term of the sequence. When I go to x equals 2, the coordinates there, that's sine of 2 over 2. That's sine of 3 over 3, the 0.047. And I can scroll my n slidey bar here to add more bullet points to that curve to show more terms of this sequence to see what they're doing. So notice how the y-coordinates are shrinking down, and then they go negative, and then they come back up positive, and then they go back down to negative territory. And if I scroll over here, they go positive again. But zooming out a little bit, notice that they're shrinking in magnitude. They're alternating in sign. They go up, they're positive, and they go down to negative, and then up to positive again. But overall, the trend seems to be the wave is shrinking in its amplitude. The peak and the trough, the top and the bottom of the wave, are getting smaller and smaller. That comes from the fact that sine is this periodic oscillating function, but dividing by x means as I scroll to the right and make x bigger, the whole fraction becomes smaller because I'm dividing by bigger and bigger numbers. And so you might be able to make a guess, a prediction from here, that these dots, these green dots, the terms of the sequence, they're going down to 0. And in fact, that is true. The limit of this sequence is 0. Here's one way to realize that. Think about what the sine of x function itself does. Here's the sine function. It itself is bounded between -1 and +1. We know that it doesn't matter what you input for x, sine of x is never going to output something bigger than 1 or smaller than -1. By the way, you should know how that's related to the unit circle. This point up at the top has y-coordinate 1, and this one at the bottom has y-coordinate -1. And remember that sine tracks the y-coordinate of points around the unit circle based on the corresponding angles. And so if I pick any point around the circle, it's never going to have a y-coordinate above 1 or below -1. That's why this bounded fact is true. That's something that you should know for that reason, not just something you're memorizing that I've stated here. But what can that do for us? Well, now that I know sine of x is bounded, think about what sine of x all divided by x does. Well, if the numerator sine is less than 1, then can't I say that this fraction has got to be less than 1 divided by x? And likewise on the other side, if sine of x is always bigger than or equal to -1, can't I say that this fraction is bigger than or equal to -1 all divided by x? I hope you can believe me that that's true. And the reason I'm saying it here is if I jump back to my graph, let's zoom in a little bit. What if I turn on the plot for the 1 over x function and the -1 over x function? These are exactly the thing on the right and the thing on the left of this chained inequality that we have. And notice that the sine of x over x function, that black dotted curve, always lives somewhere in between the 1 over x function at the top and the -1 over x function at the bottom. It's always stuck, squeezed in between those upper and lower curves. Sometimes they touch, like right there, and other times it's in the middle, like there. But it's always bounded in between them. It can't squeeze outside of that, those two upper and lower curves. And moreover, for the sequence that we're talking about, the green dots, they are therefore also bound to live in between those curves. So what can I do from there? Well, I'm going to jump to the next slide where I have the squeeze theorem stated, but also applied. When you see this stuff down at the bottom here, this is me applying the squeeze theorem stated at the top to the example we were just talking about. So let's look at the stuff down at the bottom first. We know sine is a bounded function. -1 and +1 are boundaries on the sine function's outputs no matter what the input is. Anything goes in, -1 or +1 at least and at most comes out. And therefore, no matter what n is, this has to be true. You can think of this as I divided both sides by n, or I guess not both, but all three sides, so to speak. I divided all three sides by n to get that line there. And the reason I did that is because right there in the middle, that's the sequence we're talking about, sine of n over n. Now take a limit as n goes to infinity. Isn't it true that -1 over n goes to 0 and +1 over n goes to 0? Look back at the graph. The red curve, 1 over x, that's shrinking down to 0. So I keep scrolling to the right, that's going to asymptotically approach the x-axis, y equals 0. And likewise, the blue curve, -1 over x, that's just the mirror image of it underneath. So that's also going to approach 0 upwards from below as opposed to downwards from above. That's what these two limits here say. And so where the heck are my terms of my sequence, sine of n over n? They're squeezed between those two things that are approaching 0. Where the heck else is it going to go? It's got to go to 0 too. That dotted black curve and the green dots that live upon it, they are forced to squeeze down to 0 because they're stuck between two curves that are heading towards 0 themselves. In that sense, we call this the squeeze theorem. Two upper and lower curves are squeezing something between them towards the same place. And that's what this is stated in the theorem box up here. If I have a sequence who's converging to L and another sequence who's converging to the same limit L, and I have a third sequence C that's squeezed in between the A and the B, then that sequence has to converge to L as well. So now that we have those techniques, the L'Hopital's rule and the squeeze theorem, I'm going to state some practice problems here. I suggest pausing the video for a little while and attempting these. Make some guesses of what you think these sequences are doing, converging or diverging. You can try to get at those guesses by exploring a bunch of terms, plugging in small values for n, plugging in big values for n, maybe thinking about what the graphs would look like, try to apply some of these techniques we were just talking about. But really force yourself to make an effort. Don't just play the video on and see what I'm going to say. You'll gain a lot more. You'll have deeper learning by forcing yourself to even get stuck with these examples. Don't feel like you have to solve them all perfectly well, because I'm about to show you how to do it, but force yourself to get stuck and then see what I do, because that will help you remember what to do later. Okay, here's the an sequences defined by n squared minus n. Turns out this sequence is divergent. Here's how I could explore that. When n is 1, I get 1 minus 1, so I get 0. When n is 2, I get 4 minus 2, so I get 2. When n is 3, I get 9 minus 3, I get 6. N is 4, I get 16 minus 4, I get 12. 25 minus 5, 36 minus 6, 49 minus 7, 64 minus 8, and so on. These numbers are just getting bigger and bigger and bigger. You may even notice an interesting pattern here where the difference between terms looks like I added 2, then I added 4, and then I added 6, and then I added 8. Well, that's not black magic happening there. That's just some simple algebra. Look at what an plus 1 minus an is. In other words, if I take a term, an, and I look at the one after it, the next term, and I ask what their difference is, well, it turns out it's going to be a multiple of 2. What's an plus 1? I'm plugging now n plus 1, the index, into the n's that I see up there. So this says take your index and square it and subtract itself. That comes from this. And then when I plug in the term an, I have n squared minus n. And this is going to say subtract those. Be careful about the subtraction and distributive property here. Now let me write out what that does. So n plus 1 squared minus n plus 1 all subtracted, then minus n squared minus negative n. Let's see, a bunch of stuff disappears. I have an n squared minus n squared. I have a minus n, a plus n. I have a plus 1, a minus 1, and all of that equals 2n, which is an even number. And specifically, when n is 1, that doubled is 2. That's the difference between the first term and the second term. When n is 2, that doubled is 4. That's the difference between the second and the third term. So what I'm showing you here is just, if you notice patterns like that, try to see why they're happening. Force yourself to write out some algebra or some stuff to see and confirm that the pattern you're noticing is really there. But another thing you might notice is that these terms are increasing. The sequence is increasing. It's always getting bigger. Because I can even see here the difference between the next term and the one before it, that difference is always positive. So difference, the an plus 1 minus the term before it, is always positive. That's what increasing means. It's getting bigger. And therefore, this sequence is going to be unbounded above. It has no upper cap to it. It has no upper boundary that it cannot cross. It's just going to keep increasing forever. And that's what's going to make it diverge to positive infinity. All right, for the next one, I will show you two algebraic ways to evaluate this limit. And I won't even bother plugging in some small or even big values for n, because if you do that, you'll hopefully convince yourself that it makes sense that this limit is going to be 2. Here's one way to think about this. What if I took the fraction that I'm dealing with and I multiplied in the top and the bottom by 1 over n squared? Why am I doing that? I picked 1 over n squared because n squared is the largest power that I see in the numerator. And so that's going to give me, instead, in the top 6 n squared over n squared, or 6. In the bottom, I'm going to have 1 over n squared plus 3. And as n goes to infinity, this part is going to shrink away to 0, and I'm going to be left with 6 over 3, or exactly 2. Another way to see that is I've noticed already that the highest power in the top and the bottom is n squared, and so I'm just going to compare the coefficients of 6 and 3, and that's where I'm seeing that 2. Another way to even see this is using L'Hopital's rule, because as n goes to infinity, 6n squared gets bigger and bigger, goes to infinity, and 3n squared plus 1 is also going to infinity. So when I try to evaluate this limit, I could also say I have an infinity over infinity situation. So let me take a derivative on the top and the bottom to ask which one is going to infinity faster. And then I see another situation where I have an infinity over infinity indeterminate form. I could take a limit as n goes to infinity, take some derivatives on the top and the bottom, I get a constant of 2. Here's an example where I actually definitely need L'Hopital's rule. I don't see any better way of doing this. We're asking for what's the limit as n goes to infinity of log of n, natural log, divided by n squared. Well, individually, those two pieces, the top and the bottom, are both going to infinity. Limit as n goes to infinity of log of n, that's positive infinity because its graph grows like this. And limit as n goes to infinity of n squared, that's also positive infinity because the parabola just grows. And just looking at those graphs, you can see, hopefully, that n squared goes to infinity way faster. That's faster growth than the logarithmic super slow growth. So maybe just from this, you could convince yourself intuitively and predict that this fraction is going to converge to 0 because the bottom is getting bigger way faster than the top is. But a way to confirm that is with L'Hopital's rule. So I see an infinity over infinity form here. So I'm going to apply L'Hopital's rule, take a derivative on the top and the bottom separately. Derivative of natural log of n is 1 over n. Derivative of n squared is 2n. And then when I write the next step, I'm not actually applying L'Hopital's rule. I'm just simplifying the fraction. So I have 1 over n divided by 2n, or another way to do that is divide the denominator, so 2n squared, and that's just going to straight up equal 0. I don't need to apply L'Hopital's rule again to see that. Here's another example, and in fact this is very closely related to one we did, I think it was in the previous video. The cosine of pi over 2n, just that part. What does that do as n goes 1, 2, 3, and so on? So when n is 1, what's cosine of pi over 2? That is, on the unit circle, 90 degrees, pi over 2 radians. The x-coordinate at that point is 0. What about cosine of 2 pi over 2? Well, that's pi radians, 180 degrees. X-coordinate of that is -1. 3 pi over 2, that's 270 degrees. The x-coordinate, that's 0. And then 4 pi over 2, that's 2 pi, so the x-coordinate, that's 1. And then that pattern of 4 is just going to repeat again. It's going to go 0, -1, 0, 1. And that's going to repeat, repeat, repeat. And you know what? Even if I didn't notice that it was that specific pattern, I could really just say, you know what? I know cosine of whatever is bounded between -1 and +1. Just like we were saying for the sine function earlier in this video. This is a bounded function. So, in fact, I didn't even have to notice that the pattern is this block of 4 that repeats. I'm showing you that here just to say, you know, this is something that you might have to figure out in other examples, so it's helpful to see where that's coming from. But even if I didn't notice that, I would still be able to do what we're about to do, which is apply the Squeeze theorem. So I can say that my sequence dn is stuck between +1, the largest possible value cosine could be, over n cubed, and it's greater than -1, the smallest possible value cosine could be, over n cubed. And then as n goes to infinity, plus or minus 1 all over n cubed is going to shrink to 0. This part's going to go to 0, this part's going to go to 0. So where the heck is that dn, my sequence in the middle, going to go? It's going to be squeezed to 0 in the same sense that the example we were looking at earlier with the sine function was squeezed